these two exercises are very similar. Essentially what we're asking you to do is to tune a decision tree based model. So let's go ahead and look at the second one, where we ask you to compare the performance of a random forest, extremely randomized trees, and gradient boosting trees to understand which one, or for this case to investigate which one is going to perform better for your task. So I want to spend some time talking about this, things we can go ahead and do. So we should already have the California data set already loaded. Let's go ahead and do perform a train test split. So let me just make sure. Yes, I think I have that defined. It should be over 20,000 points. That's not the case. I'll just go ahead and re-import it. All right, so I can say, let's see, do I have fetch? Yes, I do. So I can say data, kind of what we've always done before, data, and then pull out X, and pull out the target, and perform the train test split. Random state should be 0, not 0.2. Okay, did my train test split. So if I'm going to evaluate using different models, it'd be very helpful if I can construct a function to help me with that task. So I'm going to define a function called evaluate model. And what this is going to take is going to take the model, and it's going to take a string referring to the name of the model, and the param grid. Within here, in this model, what I'm going to go ahead and do is I'm going to use the random search. I'm going to use randomized search. And the reason why I'm going to choose to use randomized search is that when we're dealing with trees, there are a lot of hyperparameters we have to consider. And all these distinct hyperparameters, they're going to be its own dimension, a distinct axis in this space that we generate when we do something like grid search CV. Remember, grid search CV is going to construct an axis, a dimension for all the different hyperparameters, and construct a mesh, a grid of all possible candidates. And things might get out of hand if I have a lot of different hyperparameters, so maybe I should use something like randomized search. This idea I can construct a very large computational grid with a lot of dimensions, very fine mesh, and sample only a portion of those grid points. So it's going to take the model, it's going to take the past param grid, and CV equals 5. Let's go ahead and do end job, set that equal to 2. We want a verbose output, right? We want to get some idea of what's going on when we run this. Verbose equal to 1. We also need to change the number of iterations. So we have access to the number of iterations. I'm going to set this as a keyword argument to this function here. So I'll use 100 by default, but I can have control over that. I also need to set the random state, since it's going to have a random process going on here. I should set the random state for reproducibility. Okay. And it's going to take random search, and it's going to fit on X train and Y train. And what I want to do here is I want to print out some statistics or some results from the analysis, from this tuning process. So what are some things I want to know about when I'm tuning my model? In other words, what are some parameters or some results I want to learn from the tuning process? Well, some things that I want to know is, well, what is a training error? What is a training error? What is the cross-validation error? What is the test set error? I want to know all those 3 errors. Or in this case, since I'm doing regression, I want to know those R-squared values, so the performance metric. And the reason why I know about this is because if I have how well it performed in the training, cross-validation, testing, I can see whether I have a model that is underfitting or overfitting. Remember, the deviation between the cross-validation error and the training error is going to give me a measure of the variance. If that deviation is very small, the variance is very small. That deviation is very large, then the variation error is very large. So I have here the name. I'm just going to print that out so I know what I'm tuning. So name there. And here I can print out things like training r squared. Let's do the cross validation. So let me just copy and paste for simplicity. So CVR squared in this case, I know I can find that best score via the best score attribute of the random search. The last thing I want to print out is the testing error, the testing r squared in this case. And at the end, I want to return the model that I tuned. So let's return random search. Okay, I'm going to go ahead and focus on the gradient boosting tree. That's a more interesting one. And when we talk about these hyperparameters for these ensemble models that uses trees, I like to break down those hyperparameters into two groups. The hyperparameters that are locally to the tree, so tree specific, and those hyperparameters that are more global, that are going to affect the ensemble, that control the ensemble. For example, things like max depth and min sample split, that controls the individual tree in our ensemble. But things like the number of estimators, the learning rate, and subsampling, that's going to affect the overall ensemble. So that has a more global, more overall reach. So for this, there are different hyperparameters I can tune for my model. And as I saw before, when we're doing gradient boosting trees, I should play around with things like learning rate and subsampling. So what I could do first is I can go ahead and do a gradient boosting tree, a gradient boosting regressor, but maybe let's not fool around with things like the learning rate and subsampling. Let's just focus on maybe max depth and min sample leaf. So let's just play around with that. And n estimators, I'll just say 50 estimators. I believe the default is 10. The param grid I'm going to construct is, let's go ahead and modify max depth. Let's say 1 to 20. When we're dealing with the gradient boosting trees, those trees are weak learners, so they're going to be stumps. So I'm going to search through that very small space there. And then I'm going to search through min samples leaf. I'm going to say range, from 2 to 100 of spacing 2. Okay, let's go ahead and use that function that I defined. Probably should give it a better name than evaluate model, because it does more than evaluate. It's going to return the model back to me. But oh well. Gradient boosting trees and pass the param grid. All right, let's see what happens then. Let's run that. This might take a while. Let's go back to our tuning process. When we tune our gradient boosting tree, let's see what happened from that result. So since we've set verbose equal to 1, we're able to easily see that it took 20 minutes to train. That's quite a lot. You can see how expensive the training time can be for gradient boosting regressors, for gradient boosting trees. Remember, we have about over 20 observations, 8 features, and we chose 50 trees in our model. So it looks like the Through the process, we printed out the training time, the training R-squared value and the testing R-squared value and the cross-validation R-squared value. So it looks like there's about a 0.07 deviation between training and cross-validation. So that is our measure of our variance. So given that disparity between the cross-validation error, or the cross-validation R-squared, and the training R-squared, we have a high variance model. We have a model that is overfitting, which makes sense because hopefully we've been convinced that these gradient boosting tree models are rather powerful models, rather adaptive models. So since we have a lot of power to adapt to the data, we might run issues with high variance. And that's what's happening here. If we look at the best params, we can look at what the best parameters from our randomized search. And what we could do here in this case is notice what we did before. We didn't tune things like subsample and learning rate. So what we could do is we can retrain the model, but let's keep the best parameters that I found for the first run. So in other words, taking these best params, we'll set that for our model, and then we'll just play around with subsampling and learning rate. There's a lot of interaction between subsampling and learning rate, as we saw in the previous figures. So let's tune those two together. So that's what we're going to do here. We're going to take advantage of unpacking, this unpacking operator. So this is equivalent to manually setting those keyword arguments of min sample leaf to 52 and max depth equal to 18. I can do that very easily with a dictionary by using this double asterisk command right here. Okay, so remember that the subsample and the learning rate, those are going to range. There's going to be a fraction number from 0 to 1. So that's constrained in that way. It's bounded for those dimensions, for those length. So let's go ahead and search through that space of subsample and learning rate. Go and pass it to our function to evaluate the model and tune it. I already ran the analysis. In this case, it took about 15 minutes. And if we look at the testing and the cross-validation, so we have a slightly better model, slightly better, but it didn't really help out in terms of variance. Our training error is slightly higher, so we probably have the same level of variance. We can look at the best params, and notice the best params was one in which we subsampled, we applied subsampling, and we had a very low learning rate. In this example here, I try to repeat the process. In this case, I tune just max depth, subsampling, learning rate, so all those three hyperparameters at the same time. Forgot about min samples leaf. I said, you know what? Let's just focus on max depth. In that case, it took about 30 minutes to train, and the model's performance is pretty much comparable, slightly different, slightly worse. If we look at the test set error and the cross-validation, you can see how tricky it is to tune these trees to get the most out of them. These are some more examples I did here. One strategy is we can use a small number of estimators, let's say like 10 in this example here. It's going to be faster to train. And then once we've trained that model, we can look at the best params and retrain the model, keep those best params, but ramp up the number of estimators. So we're trying to exploit this behavior that we saw up above, that in general increase the number of trees, increase the number of estimators will lead to a better model. So essentially, one way you can view it is we're finding the best hyperparameters at this space here, and then we increase the number of estimators to have a lower error. So see if you can do better than what I have, and try it out.